Our discussion today is lecture number 10. Lecture number 10, and our discussion will be effect of temperature on rate constant of a reaction, and it is explained by Arrhenius equation. This equation is very important who are studying the chemical kinetics, as the rate constant varies very rapidly with the change in temperature. Generally, the rate constant increases exponentially with this rise in temperature. So you can see in every case in your daily life, say with the rise in temperature, rate of any reaction, any process will rapidly increase. You may consider the aging process. In the aging process is highly increased in the rise in temperature, means in summer tropical countries where temperature is very high, hot region, the persons easily becomes old. But in cool countries where temperature is low, the rate of this aging process is also low, and so the aging process is being delayed and the man looks young even at older age. So it is the daily phenomenon, not in chemistry, but in our every daily life. You can see whenever you rise the temperature, the rate of this process will be accelerated, and rate actually approximately becomes double to treble by the rise of a 10 degree temperature. Say means the rate of any process generally becomes the double when the temperature is increased by 10 degree. Say rate is found to be say 10 or 15. If you rise this temperature by 10 degree, then it becomes 30. In some cases it becomes 45. So the range of the increase of the rate of a reaction by 10 degree rise in temperature lies between 2 to 3. And you see, if we consider the different reactions, we may consider the 3 types of reactions. Say homogeneous thermal reactions, thermal explosion reactions, and lastly we may consider the enzyme catalyzed reaction. Say type of reaction number one, it is thermal homogeneous reaction, and here it is T in Kelvin, and here the rate of this reaction, and it will start from 0 and increasing by this way. So, with the rise in temperature, rate of this process for this type of reaction increases. And another type, here rate, here T, and it is the thermal explosion reaction. So it also starts at 0, theoretically starts at from 0 origin, and then increases, and after certain temperature, whenever the reaction attains a certain temperature, it actually explodes, means the rate becomes tremendously high. Up to this type, it follows like this, but whenever the certain temperature is attained, the rate of this reaction becomes tremendously high, leading to explosion. Here the example is hydrogen plus iodine and giving you twice Hi. All are in gaseous phase, homogeneous thermal reactions, all are homogeneous, means all the reactants and products are in the same phase. And here thermal explosion, say explosions of this TNT, trinitrotoluene, or say up to certain range, say hydrogen plus bromine, all are in this gaseous state, giving you this twice HBr. Up to certain temperature, it increases smoothly, and after certain temperature, the reaction becomes tremendously high. And the third type, very important one, here also rate, here temperature T, and it is enzyme catalyzed reaction. Enzyme catalyzed reactions. You have already, I think, heard of this enzyme. Enzyme is catalyst, very specific, very effective, and small amount of enzyme can catalyze a large amount of this reaction. And in this case, it is like this, increases smoothly and attains maximum. Here you can call the R max at this temperature, and the temperature is about 35 to 45 degrees centigrade, or maybe extended to 55 degrees centigrade. After that, the rate is decreasing with the rise in temperature. Actually, these enzymes are present in colloidal state in solution, and whenever the temperature is increased at a high temperature, the colloidal state is destroyed, the enzyme coagulated or sedimented, and the effectiveness of this enzyme is also destroyed. I can, for the sake of curiosity, I can show you one enzyme catalyzed reaction. It is highly specific. As you see, one key can open one lock. One enzyme can catalyze only one particular reaction. Say urease, one catalyst, enzymes. This urease decompose this urea. Decompose urea, say CnH2, CO, NH2, and whenever this urease catalyst is used, it forms this twice ammonia plus water. Ammonia and plus carbon dioxide. And you can see in your daily experience, whenever you enter in an urinal, you get the smell of this ammonia. Ammonia is coming by the decomposition of this urea, and the catalyst is enzyme catalyst, and this enzyme is urease. In human body, you will be surprised to know that we swallow starch. We swallow starch. Starch means we can write C12O10 H10 H10O5 and N. It is starch. Starch we consume in the form of carbohydrates, say potato, rice, etc. Every foods, almost these carbohydrates are with starch. And the starch in our human body, this enzyme diastase, one enzyme, diastase and one molecule of water, and it forms maltose, say C24H22O11. It is maltose. The starch is converted into maltose by the use of this diastase. It is also your daily experience. Whenever you cannot digest this starch, doctor or physician, health provider will give you one bottle of digestive solution which contains this diastase. Diastase actually helps to break down this starch into maltose, and after that maltose and here another enzyme, it is maltase, and one molecule water is added, and it is the C12 twice it is 12. It is 12. Carbon remains same. So it is the 6 twice H 12 O 6 11 and 1 12, so 12, and it is glucose. Everyone knows the glucose which we intake generally whenever we feel thirsty in summer. And here it is another enzyme, gymase, present in yeast and forming this alcohol plus 4 carbon dioxide. So this alcohol ultimately is being produced from the starch by the use of this so many enzyme catalyst. And actually you see this alcohol by means of ATP produces this energy in our body, which supply the energy in our body and by which we can work very efficiently. So it is the enzyme catalyst. So 2 examples I show the enzyme catalyzed reactions. So there are so many reactions, enzyme catalyst. Nowadays, catalyst playing a dominant role in regulating the kinetics rate of this process or chemical process. Now, so approximately I can say the rate is increased by 2 to 3 fold by the increase of 10 degree temperature. But actually a rate equal to the rate constant of this reaction and the concentration of this reactant N. You have seen this rate depends on so many factors which I have discussed in my early classes. But most important are the 2, concentration of the reactants and the temperature. Whenever we study the effect of concentration on this rate, the temperature we shall keep constant. Whenever we shall study the effect of temperature on this rate, then concentration is to be fixed, keeping the volume of this reaction vessel fixed, so that concentration does not change with temperature. So from this, if concentration is N equal, and you have already learnt N equal to 0 means 0 order reactions, N equal to 1 means first order, N equal to 2 means second order, N equal to 3 means third order. More than third order is not possible. So we can write this rate. Rate is proportional to rate constant of this reaction. If the rate is increased by 2 to 3 fold by 10 degree rise in temperature, rate constant will also rise double to triple, 2-fold to 3-fold by 10 degree rise in temperature. So one very popular term, we shall actually study the effect of temperature on this rate constant, and whenever the rate constant is increased, the rate is also rate of this reaction is also increased. So one very popular term, though it is approximate, the temperature coefficient. One very important term is the temperature coefficient. Temperature coefficient is denoted as K T plus 10 divided by K T, and it is approximately 2 to 3. So by the rise, Kt is the rate constant of this reaction at temperature T. Kt plus 10 is the rate constant of the same reaction at a temperature T plus 10, it means 10 degree. So this ratio will give you how much times the rate constant is increased by 10 degree rise in temperature. Whenever it is twofold, means this temperature coefficient becomes double. Whenever it is 3, it is threefold, or any normally. In general, it may rise 2 to 3, say 2.1, 2.2, 2.5, 2.7, and so on. So it is the temperature coefficient of a reaction, which is also very important or popular term. So long we are discussing the qualitative features of the effect of temperature on this rate and hence this rate constant. Now I will be coming to describe the accurate relation between the temperature and rate constant. Accurate relation between T and K, temperature and rate constant. And from the observation, various type of observing the reaction rate at different rate constant at different temperatures, Sante Arrhenius proposed one very important equation relating temperature and the rate constant of a reaction. And this one is this K equal to A into e to the power minus EA by RT. A and EA are considered or assumed temperature independent. These are the constant of a particular reaction. R is universal constant whose value is 8.314 joule per mole per Kelvin. So these two are constant for a particular reaction. R is also constant. So the variables are K and T. From this relation, you yourself can consider the effect of temperature on this rate constant is exponential in nature. This A is called pre-exponential pre-exponential factor. As it is placed before the exponential term, so it is called the pre-exponential term. It is related to this frequency of the molecules which are colliding during the process of this reaction. So it is sometimes also called the collision factor. Collision factor, or sometimes called Arrhenius factor. Arrhenius factor. So this A is having the different names, but it is related to this frequency of collisions of these reactant molecules. Means frequency of collisions of binary collisions. Binary collisions are very popular. Ternary collisions very rare, and quaternary four-body collisions impossible. At a time, two bodies can collide, three bodies also collide very rarely, and four-body collision is very, very rare. So it is related to the collision factor, collision frequency. Collision frequency is the number of collisions made by the molecules in unit volume, in unit time, in 1 cc volume, in 1 second time. This is very, very high, very, very high. About this value almost 10 to the power 27 or like that molecules collisions per cc per second. And EA is a very important term in the Arrhenius equation and also in chemical reaction. And this is called the activation energy. Activation energy of the reaction. Activation energy, what is meant by the activation energy? Whenever we shall study the collision theory, then we may see the collision is the precondition for a reaction. The two molecules, say hydrogen and here I2, these are the two gaseous state. These two react to give you this HI, hydrogen iodide. For the reaction, first very important state is that the two molecules collide. Whenever the two molecules collide, they come each other, they come close to each other. And whenever they come close to each other, then there will be chance for this reaction. It is not that all the collisions between the two molecules will give you the product. They should be properly aligned. One condition is properly aligned. Whenever they are colliding, they should be properly aligned. Alignment is there, oriented. Proper orientation is required. And second, say here is H and here is H plus, and here I, they are, it is coming in this fashion, it is coming in this fashion, they are colliding head-on collision. Head-on collision will be the proper orientation for the reactions to give you the product. Not on if every collision would be effective, then the K must be equal to A. A is very high. So rate of this reaction should be of this magnitude, but it is not that. Rate of this reaction per cc per second is very, very small in comparison to the collision factor. So there must be another factor, another term which is responsible, which prevents the every collision not producing the product, and this is the activation energy. The reactant molecules not only collide in proper orientation or proper alignment, but they should attain a minimum certain excess energy, in order to enter into the chemical world. Chemical reactions only occur. Whenever the reactant molecules acquire excess minimum certain amount of energy, and that minimum certain amount of energy is called the activation energy, EA. Unless and until the reactant molecules can acquire the excess energy EA, the collisions is not fruitful. Whenever they are proper aligned, whenever the reactant molecules have minimum excess energy, activation energy, acquire this activation energy, we call those collisions are effective collisions. Those collisions are, we call effective collisions, which lead to chemical reaction. I shall again talk about the activation energy. A certain minimum excess energy is urgently required for the structural orientation of the reactant molecules, rearrangement of these atoms within the molecules, certain change in internal vibrations. All these factors require a certain minimum energy for undergoing the chemical reactions. Reactions is nothing but the breaking of the old bonds and making of a new bonds, and this is the chemical reactions. Now I am coming again to this Arrhenius equation. This one equation, this is equation 1 as Arrhenius proposed. If we take this log on both sides, natural log, then it is ln k equal to ln A and minus EA by R into 1 by T, equation number 2, taking this natural log of both sides, E base. So in this case, ln k and 1 by t, these two are the variables, and rest ln a, ea, r, these are constants. This equation is widely used to determine the activation energy of a reaction. Actually, this is the only way out to determine the activation energy of a reaction. Only for those reactions which will obey the Arrhenius equation. This we call the Arrhenius type of reaction. Arrhenius type of reactions. So, if you like to determine experimentally the activation energy of a reaction and also frequency factor, these two are the important term of a particular reaction. These two are constant for a particular reaction independent of temperature, as we have assumed. So, what we shall have to do? At a different temperature, the rate constant of these reactions are to be determined by experimental method. We have seen how the rate constant of a reaction is determined, and that determination we have discussed in a particular temperature, keeping this reaction vessel in a thermostat of fixed temperature. So, in this case, we can determine this rate constant of this same reaction, the same process at a different temperatures, keeping the reaction vessel in thermostat at different temperatures. So, 1 by T and ln k, these two are the variables, and this equation is equal to y equal to c minus mx. This is the independent variables and this one is the dependent variable. So, whenever we plot 1 by T, 1 by T, and here it is ln k. By determining the rate constant of the same reaction at different temperatures, we can make a table, and from this table, that data of this table is reflected in a curve, and this curve will be straight line having intercept and negative slope. So, this will be like this. We shall not experimental plot. So, suppose these are the experimental point. These are the experimental point, and we cannot extend this plot, extend this straight line to cut this y-axis. It is not possible here. 1 by T equal to 0 means T equal to infinity at infinite temperature. You cannot do any experiment to study the rate constant of a reaction. So, it remains blank. However, we can extrapolate, extend this plot to cut this y-axis, and the slope, this is theta. So, slope will be equal to tan theta, angle subtended at the right side of this straight line, and this one equal to minus Ea by R. R is known to us. So, activation energy of that reaction could be determined from the slope of this curve. We also determine the activation energy intercept. This is intercept, and intercept is ln A, and from which we also calculate the frequency factor or Arrhenius constant or free exponential term of this reaction from this intercept. However, one experimental difficulty I can show you, it is not so easy to draw the exact curves. Suppose we are studying the 100 Kelvin, 300 Kelvin, 310 Kelvin, 320 Kelvin, and so on, 300, 330 Kelvin. But 1 by T, whenever 1 by T we consider, these points will be very close to each other. These points are very close to each other. And from those points, it is very difficult to extend the curve to cut this y-axis. This is the trouble for doing this experiment. Very, very difficult job actually. Rather, approximately activation energy we can determine by determining the rate constant at 2 temperatures. Say in that case ln K2 by K1 equal to ln A will cancel, and here it is EA by R into T2 minus T1 divided by T1 T2, and equation number 3. K2 is the rate constant of this reaction at this temperature T2, and K1 is the rate constant of the same reaction at the temperature T1. So only two rate constants at two different temperatures of the same reaction could provide the value of EA. I can show you several problems. Say milk is destroyed or sours whenever kept at 30 degrees centigrade. But whenever it is kept in a freeze at 5 degrees centigrade, it sours, means it spoiled at 1 week time, 7 days. And you are to calculate the activation energy for the souring process of this milk. Say one problem, you can do it in your home. One bottle milk sours in 1 day when kept in room temperature of 30 degree centigrade. But if the milk is kept in a freeze, FRIDG freeze at 5 degrees centigrade, it sours in 1 week time. 1 week time. Calculate activation energy of the souring process of milk. Souring process of the milk. You can do it. K1, and here it is K is inversely proportional to 1 by T. T is the souring time. Greater the value of T, less will be the rate constant of the souring process. So this one we can write ln T1 by T2 equal to EA by R into T2 minus T1 divided by T1 T2. T1 is T1 given 1 in 1 week and another is 1 day, and T is also given. It is the 30 means 310, it is 5 means 278. So R is known, EA could be calculated. You calculate this at your own home in your leisure times. Solving the problems in physical chemistry are the backbone of learning the physical chemistry. If you fail to solve this problem, means you cannot understand the text underlying this chapter. So I always advise you to do problems as much as you can, different types of problems, so that you can manage this chapter very easily. It is that for one day it takes time to solve this problem, but it is not the wastage of time. You are thinking and you are searching in your text to solve this problem, and this will benefit you to learn the chapter more closely, more accurately, more intensively. So now another question. How the Arrhenius equation is coming up? Has it any theoretical basis, or simply the observation from the observation for the different reactions at different temperatures? Yes, it has a theoretical basis. It could be formulated from a very famous equation, Ventop equation, which I have discussed in chemical equilibrium, effect of temperature on this equilibrium constant of a reaction. Suppose we are considering the reversible reaction, simple reversible reactions, unimolecular both ways. Here it is K1 the rate constant, here it is the reverse one the rate constant for this reverse reaction or backward reactions. This is the reversible reactions. And the Ventop equation relates the equilibrium constant of this reaction with the temperature. And you see our Arrhenius equation is ln k equal to ln A minus EA by R into 1 by T. There is some shortcomings in this equation, as we have assumed this A and EA, these are temperature independent, but it is not always the case. In many reactions, activation energy depends on temperature, and collision frequency of collision certainly dependent on temperature, but that dependency is not so high with respect to this Arrhenius equation. So if we do this differential form with respect to T, differentiating this equation with respect to T, then we have d ln k divided by dt equal to EA by R T square. And this is the very 1 by T with respect to differentiation T. So it becomes minus 1 by T square, 1 by T square minus minus a plus, and so this one is coming here. This is a very important form of this Arrhenius equations. I will show you some problems where activation energy depends on temperature. In this case, no assumptions has been made that activation energy and frequency factor is temperature independent. So this is more general than this one. Here no assumptions made. No assumptions is assumed that activation energy is independent of temperature. So this is the exact form of this Arrhenius equation, more general. And we like to formulate this one from Venthoff equation. Venthoff equation, and it is the equilibrium constant equal to K1 by K reverse 1. Equilibrium constant. So the Venthoff equation which relates the equilibrium constant with the temperature is d ln equilibrium constant divided by dt equal to delta E divided by R T square. This delta E is the heat of reaction. Delta E is the heat of reaction. Delta E is the heat of reaction. Whenever it is positive, whenever it is negative, exothermic. Whenever it is positive, endothermic. And in some very rare cases, this delta E also equal to 0. As you see, in a chemical reaction, breaking of the old bonds and making of the new bonds involves the energy. So either energy is released, in that case delta E is negative and we call the exothermic reactions. Whenever the energy is absorbed for these reactions to continue the reactions, it is endothermic. Delta E equal to positive. And in very rare case, the energy required for breaking the old bonds is exactly equal the energy released for making the new bonds. In that case, delta E equal to 0. which is very rare case. So, this delta E here, delta E we can write Ex minus Ea minus Ex minus EB. Ex is the energy of this activated complex. Say A reactant and gives you this X, it is the activated complex. And then it breaks down to give you the product. Here the activation energy equal to EA 1 and here it is EA reverse 1. X is called the activated complex. Whenever the two molecules collide, they make an impact coming close to each other, makes a loose association of the reactant molecules, and this loose association, transit association, is called the activated complex. Say one example, say H plus I, hydrogen plus iodine, and this will collide in proper alignment and attains this activation energy, and they make a transit association. And it is a activated complex. It is not the independent entity, but some sort of loose association occurs among the reactant molecules, and then it breaks up. Here I plus, here H plus I, product. It is product, it is reactant, and it is the activated complex. So whenever activated complex, what will be the nature in a graph? What will be the graph? Say here the energy here the reaction coordinate, energy of the reactants, products, and activated complex, and it is the reaction coordinate. Reaction coordinate is a qualitative term. Whenever the two molecules are approaching closely, their distance between the two, their structural transformation, their internal vibration of these reactant molecules, means it is the path by which the reactant molecules are converting into product through the transient association, and that path is given by the reaction coordinate, and this term is qualitative in nature. So what will be the curve? But it is highly, this curve which I like to draw is also qualitative, but this curve is very useful to explain the activated complex activation energy and the process of this reaction. Suppose here it is EA, activation energy. Here EA means energy of this reactant, energy of the reactant EA. It is the energy of the product. As the reaction goes, as the two molecules are coming close to each other, the reaction coordinate increases, energy also increases, and here it is the EX. EX means energy of this activated complex, which is the transient association of the reactants, which is in the way to proceed the product, to form the product, and then it comes to this one. And it is the EX value is this one. This value is EX, and this is the energy of the reactant molecule. So reactant molecules are having certain average energy, and that is EA, and this one is called EA1. Activation energy for the forward reaction to reach from A to X. This is the excess energy. This excess energy always required for the reactant molecules to reach the top of this hill or cross this energy barrier. This is the energy barrier. And after that it is coming to this EA-1. It is the activation energy for this reverse process. So you can see the reactant molecules does not straightway transform into product, not from this to this, not straightway the reactant molecules goes to product, to form the product. They will have to pass, they will have to cross this energy barrier, then only it can transform into product. So this is the energy barrier for the forward reaction, this is the energy barrier for this reverse reactions. So actually what I say, suppose here is the plain land, here is the hill, and here is the another plain land. Suppose one person trying to reach from this to this. From this to this man will go one plain land to another plain land. But this person cannot go straightway to this plane. They will have to cross this energy barrier. This have to cross this energy barrier. Then only it is this person will have to climb at the top of the hill, then it comes to this another plane. So it is the barrier of height, and is the energy barrier. It is height barrier, it is energy barrier. It is also sometimes called the energy of this hill. So this one we can write. This one we can write this energy A1, activation energy for the forward reaction, and this one we can write activation energy of this reverse reaction. So instead of writing this delta E, we can write this stuff in terms of this activation energy. So this is a very important graph to show you the concept of this activation energy. It is the high energy hill the reactant molecules have to cross. Now you can put instead of this one, this value, and instead of this and this value. And we have got d ln k1 by k reverse 1 into dt equal to EA1 minus EA reverse 1 divided by RT square. So naturally it is the combination of two equations. If you separate these two equations, one will be coming up for the forward reaction, another will be coming up for the backward reaction. So in this case, d ln k1 by dt equal to EA1 by RT square, T square plus C. There will be some constant C. And it is the equation for the forward reaction. And in this another d ln k reverse 1 divided by dt equal to EA reverse 1 divided by RT square plus C. C is the constant. Same value of C, so that whenever we difference, we subtract from this one to this one, this C will cancel. But Arrhenius assumed that C equal to 0. Arrhenius himself assumed C equal to 0. So in this case, C equal to 0. So this is for the forward reaction, and this is for the reverse reaction. So in general it will be, in general we can write d ln k divided by dt equal to EA by RT square. So this is the Arrhenius equation, which is more general. No assumptions have been made whether the activation energy is temperature independent or dependent. Now I like to show you the prominent features of this Arrhenius equation. Prominent or salient or characteristic feature. Characteristic features of Arrhenius equation. Arrhenius equation, characteristic features of this Arrhenius equations. So suppose A and the another equation k equal to A into e to the power minus EA by RT. This is equation number 1. This is 2 and this is 3. So we consider these three equations. From this one, you can see the 1 by t remains in a exponential term. It means whenever the t, say k equal to a into e to the power minus Ea by RT. Ea and A, these are temperature independent, it has been assumed. So with the rise in temperature, this value is decreased, negative sign, so this value is increased. You can write this one, say A divided by e to the power Ea by RT. Whenever temperature is increased, this value is decreased, denominator is decreased, this one is constant, so this term is increased. And this increase of rate constant with the rise in temperature becomes an exponential pattern, means increases very rapidly. And the equation and the feature number B, feature number 2. From this again you see activation energy for the reactions having higher activation energy, for reaction having large activation energy, activation energy means EA, large activation energy, means very large amount of energy required for the reactant molecules to cross this energy barrier, to cross this top of this energy hill. So in that case, only fewer molecules can achieve that passage, and whenever the fewer molecules can reach this activated state, the rate will be slow. So for reactions having a large activation energy, reaction is slow, means higher the activation energy, the rate constant is low, and whenever the rate constant is low, rate is also low, as rate is directly proportional to this rate constant. So this is the B, and reverse is also there. Whenever for reactions having small activation energy, more of the molecules can easily cross this top of the hill, and there will be rapid reactions. The reactions will be fast. Reverse way, if we think. Then C, temperature coefficient. Temperature coefficient is this one. If we express this temperature coefficient, Kt plus 10 divided by Kt, it is the temperature coefficient of this reaction, equal to A into e to the power minus Ea by R into T plus 10 divided by A into e to the power minus Ea by RT. Ratio of these two values, one is T plus 10, another is T. If we solve one, then A cancels, and e to the power Ea by RT minus Ea divided by R into T plus 10. So this temperature coefficient Kt plus 10 divided by Kt becomes EAR constant. So it will be e to the power 10E 10 EA divided by RT into T plus 10. I do not show elaborately this process from this to this, you can do it yourself. So this is the expression of this temperature coefficient in terms of this activation energy. Now we see how for the large value for 1, for high value for EA large, for a reactions having EA large, whenever EA is large, then this ratio is also high. Means K temperature coefficient is also large. What does it mean? The reactions whose activation energy is very high, then small rise in temperature increases the rate constant of this reaction to a large extent. What does it mean? Means this reaction is very sensitive to temperature. Rate of this reaction is very sensitive to temperature. Small rise in temperature, EA is very high, so small rise in temperature can create the temperature coefficient is also large. And high value for large value of activation energy, the reactions is very sensitive to temperature. And B and 2, here also the temperature. At high temperature, for the same reaction, for high temperature, for the same reaction, T is here, the temperature coefficient is small. Means the temperature coefficient is rather comparatively larger at lower temperature than at high temperature for the same reactions. If you do this experiment 310 and 610, then here the temperature coefficient is large, here the temperature coefficient is relatively lower value. Means with the high temperature, as the temperature is increased, this one becomes less sensitive to this temperature. And the last one, EA equal to 0. Say for the reaction having activation energy nil. No activation energy is required for this reaction to undergo to convert into product. And there are several types of reactions. Free radical reactions, chlorine dot plus chlorine dot equal to Cl2. There are so many reactions. CH3 dot plus CH3 dot and giving you C2H5H6. And also you can write CH3 dot plus chlorine and giving you CH3 Cl. So this free radical recombination, for this free radical recombination there is no need for the activation energy to undergo the reaction. So EA equal to 0. So EA equal to 0 means this term, whole term becomes 1. And when whole terms becomes 1, this K equal to A. K is equal to the frequency factor, which is maximum optimum. Means reaction proceeds at an optimum temperature, at optimum rate. Reaction proceeds at an optimum rate and no temperature effect for this type of reactions. For this type of reactions. So this is all about the discussion of Arrhenius equation, means effect of temperature on the rate and hence this rate constant. In my next class, I will show you several problems and examples in which the rate constant decreases with the temperature. Rate constant decreases with increase in temperature. I will show one example. Not only that, I will do some problems and also very difficult problems which have been set in different IIT-JEE, NEET, GATE and all India university exams. So this is the today's lecture on Arrhenius equations. I thank you all who are for this long time you are watching my video. I will try to give you an impression of this subject, and for that I request you all to do the problems. Without doing the problems, physical chemistry you cannot understand. Suppose one example, one important talk I can say. Suppose you are reading this book, exercise book, but you are not doing this exercise. You are reading the exercise book only. You are not doing this exercise. Then your health will not improve. Your health will not improve. For the improvement of your health, you need to do the exercise, not the reading only. So this is also the case in case of physical chemistry, where you have to do some problems as much as you can. Thank you again. I thank you all.